Today we're going to be talking about multiprocessing, what it is and how it can make your life better. Let's go. To go back to some history, modern processors often come with more cores rather than small number of fast cores. That's because of something that happened in the 2000 era, where chip designers were increasing the amount of transistors and the clock rate on the chips. And what they found was that the heat dissipation, or the heat generated by that chip, increased exponentially as a function of those two variables, clock rate and transistor count. And so what happened was IBM actually came up with a good idea to have, rather than one fast core, a few slower cores that were able to be cooled. And this is actually a huge breakthrough because they were able to increase the amount you could process, like raw computation power, while still maintaining a coolable temperature. This allowed for something called multiprocessing, where two things could run at the same time. Not to be confused with concurrency, where two things could share CPU time and make it look like they were running at the same time. Over the past 20 years, applications have slowly started using multiprocessing to speed up their user experiences, as taking advantage of the full hardware allowed for better performance. Today, it's important for you to learn how to use multiprocessing, otherwise you'll be hitting a performance wall too, trying to fit all those tasks onto just one core. So I might have convinced you that multiprocessing was a good idea, but before you pull the trigger on it, there's a few things you should know. Sometimes your task isn't actually parallelizable. Take, for example, a restaurant that cooks chicken. Yes, just chicken. A customer orders a chicken parmesan dish, but in order to make the dish, you must first season it and then cook it. This task is not parallelizable because you cannot both season the chicken and cook the chicken. Therefore, you're limited to what you can parallelize here. Another example is when you have a situation where a customer orders 4 dishes of parmesan and you have 4 chefs. Now this should be pretty easy. Each chef makes one dish, but let's say you only have one cutting board and one knife. You can have a situation where one of the chefs picks up a knife and another chef picks up a cutting board, and they both sit there waiting for the other piece to be available to cut the chicken. This is called the deadlock state because both people or processes are waiting on each other for a resource that they will not give up. Now let's say you got each chef their own cutting board and their own knife. How do you actually go about multiprocessing? Well, let's jump into text editor to find out. Alright guys, so we're in the terminal. I'm going to open up my preferred text editor, VS Code. Yes, welcome. Alright, and I'm going to make a file called multiprocessing.tutorial, mp.tutorial. And in here, we're just going to import a few libraries, and I'll explain what they mean in a minute. So multiprocessing, we're going to import from that library or my package process. Then we're also going to import time. And in our, and we're importing time because we want to time how fast these things take, or how fast we can make these things go. So in this program, we're going to define some chefs, and each chef can kind of like work independently, and we're going to think of chefs as a process, and so they're actually going to inherit from the process class. And then in here, I like to always define a init method, just to showcase exactly what it is we're doing. And in the init method, if you choose to define it, you must instantiate the process variables and pass a reference to yourself in order for the process constructor to set all the necessary things to make your process runnable. And then you also need to define something called the run method, and this is the method that gets forked when you call when you tell the process to start. And so usually you define this, and in here you can put exactly what it is you want it to do. So you can, let's see, you can do stuff. In this actual example, we're going to have a chef cook a chicken. So I'm just going to define a method called cook chicken. And in here, literally not going to do anything super cool. I'm just going to make a chicken, and it's currently not cooked, and so it's going to be all zeros. I'm going to make it 1,000,000 long because it has 1,000,000 cells, and so it's a 1,000,000 zero array. And I'm going to just go through this array and cook the chicken. So for I for piece or cell in chicken. Yep. Cell equal to 0 or 1, meaning it's cooked. And so then we're going to return the chicken. And there's no really point to returning it, but whatever. So in our run method, we're going to cook the chicken, and that's it. It's done. I think we can also print out that we finished the job. So chef has finished cooking the chicken. Okay, so that's all you really need to define for a process. And again, there's a lot more to the process class I'll be going over in future videos, but this is just to get you sort of started. And this isn't really too useful because we're not actually saving this or returning the chicken that we made here. And so cooked chicken will be created and cooked, but then we don't actually return it because there's no such thing as like returning off a process in this sense. What you use is something called interprocess communication, and this is something we'll go over in future videos, just because there's so much to it. But for now, it just does an isolated task that doesn't have anything to do with the main thread. And in here, we're going to actually run this process. And so really all you need to do to run the process is to create the process object and then just call start. And literally that's all you need to do. This technically works, but we're going to want to wait for it to finish. And so what you're going to do is you're going to keep that object reference to the process, and then you're going to start it here, and then wait for it to finish here with a join method. And so all the join method does is it will make the main thread wait before executing the next line, which we'll say is a print statement that says that all the chefs are done. Lastly, okay, actually, let's just run this. So I'm gonna do Python and tutorial. So the chef finished cooking the chicken, and then after that happened, we printed out the next line. All the chefs are done. So obviously, we're not just gonna cook one chicken in this kitchen. We're gonna cook multiple chickens. The first thing I want to do is we want to actually time how long these things are taking. So we're going to make something called just a timestamp, set it equal to the current time, and this is Linux epoch time, and that's like time since I think January 1st, 1970. Could be wrong, could be 1980, but whatever. The actual date doesn't really matter. After this is all done, we're going to just print out the time taken over here. Minus time dot, oops, actually that's wrong. Time dot time minus TS. And I'm also going to round this to the 100th place just so it's easier to read. And let's give that a shot. So it took 0.02 something, I should put units, seconds, to run that. 0.03, 0.02, cool. So that's the initial benchmark for how long this sort of method takes to iterate through 1,000,000 and set them all to 1. That's pretty fast. The next thing we want to do is see if we can do this any faster. In fact, I might actually make this a little harder. Let's see if we do this. All right, 0.19 seconds. That's a lot. So this is actually 10 million. So let's instead make 4 chickens after each other. So we're just literally going to copy and paste this 4 times and see how long this takes. And that's 0.71 divided by 0.19. That's 3.7 times longer to cook a chicken, then cook the next chicken, then cook the next chicken, then cook the next chicken, one after another. And that kind of makes sense. It's around 4 times. And this is all, it's not exact numbers because I have a bunch of processes running on my computer in the back. So these aren't the only processes running. And so times can vary, and these will vary on your computer as well. So that's cool, but we're not actually doing any multiprocessing here. We're kind of just waiting for one process to finish, then doing the next process, then waiting for that to finish. Essentially, this can all be done in the main thread. We don't even need multiprocessing. So in order to make this multiprocess, we're going to make a chefs array.
and we're going to go through and add a bunch of chef objects to this array. So for I in range 5, we make 5 chickens. Chef, we're gonna have 5 chefs. Chefs.append chef. Oops, that has to be created. So you're gonna append an object to the chefs array, and then for chef in chefs, we're going to tell them all to start cooking the chicken. So I'm going to put this method here, and then of course we have to wait for them all to finish. So we're going to do for chef in chefs chefs.join or chef.join. And so this will let them all start, and then we'll wait for all of them to finish and see. Let's see how long this takes. In our previous benchmark, actually, I think we cooked 4 chickens last time. Yeah, that was 1, 2, 3, 4. Yeah, that was 4. So we're gonna do 4 chickens, just to keep this all even and see what kind of speed up we get. Uh-oh, it looks like I forgot something here. What did I forget? All right. So 0.21 seconds. So that is a huge speed up. It's actually the same amount of time it takes to cook 1 chicken, approximately. And so we get it's good that we can cook these all at the same time, and yeah, it saves a lot of time to use multiple processes. So of course, when you hire more chefs and you tell them to all cook chicken, it's going to be a lot faster. Now, there's a limit to actually how many chefs we can use, and this is limited by the number of cores you have. And if you remember what I said earlier, cores allow you to do multiprocessing. And so you can actually check how many cores you have by doing print multiprocessing.cpu count. And this will print out the number of cores we have. I'm just going to label that. Let's see how many cores I have. So I have 12 cores. And so essentially I can have 12 chefs at the same time. And let's see what kind of speeds we get here. So it's a little slower, and that kind of makes sense. When you have more processes running, there's a lot of context. There's a lot of usage in terms of memory. This is 10 million, essentially, bytes in memory, and these may not be able to fit into some of the caches that are close to the CPU, and so you'll get a lot of cache misses, which take extra time. And so you'll see this number go up. But generally, it's quite linear, and I've actually graphed it out here. 1 second. You can see the increase in time it takes is actually in the beginning when you don't have too many processes running. So this is the number of chickens you're cooking, and this is the time it's taken. It actually does not increase until you get to around like 5 or 6 chickens, and that's when you start getting more cache misses. And yeah, keep in mind you have other processes running on this computer. So what happens when you actually have more processes running? Well, before I show you the graph, you kind of already got a sneak peek. If I have 24 things running and I only have 12 chefs, it actually takes around double time to cook. And this kind of makes sense. So yeah, of course we're having a lot of cache misses here, so we're compared to this number, it's around double. 84 divided by 43, yeah, around double time taken. And so of course, all depends on the processes currently running. These aren't exact numbers. And I can increase the number that we do, so we can do 48. See how long that's taken. 1.85, and that's like around 2.2-ish longer, and that also makes sense. And so if I plotted this up into 128, and you can see it's approximately linear, and that makes sense because when you have more chickens to cook, it can take a lot longer. And you kind of see that it is a little bumpy, and that can be because when you have certain amounts of processes running at certain times, it can be different, but approximately it's linear, which is what we expect.
So that's all for this video. Leave a like if this helped you, dislike if it didn't help you, and if you have a suggestion for what you want to learn next, or a suggestion on how I can do teaching videos differently, like if you thought the first part was too much fluff and you just want to get to the coding parts, or you want more in-depth coding parts, let me know. I really take feedback into consideration for how to make these videos. And yeah, I hope you like my first video on YouTube.